Welcome. Let me propose a definition of geodesic flow and sectional curvature for finite abstract simplicial complexes. Maybe I was playing too much with these Shashibo cubes. Here is a cut one, so that one sees the structure better, but it is a notion which I think is very natural, hopefully can produce some results. First of all, we start with a finite abstract simplicity complex, which is a finite set of non-empty sets closed under the operation of taking finite non-empty subsets. And then we have also the dual complex, which is not a simplicity complex, but it's naturally a CW complex. So the elements in GEDs are called simplices, and the dimension is just the cardinality -1. And so the number of vertices, which are the zero-dimensional simplices, is F0, then the number of edges, so on. The number of facets is FQ, the q-dimensional simplices. Now for the dual complex, it's just reversed. So the number of vertices is FQ, which is the facets, and F0 is the number of q-dimensional cells. So these cells are no more simplices. Maybe kind of just an example here. This is the, one of the smallest simplicial complexes, which is a q-manifold, the icosahedron, and then the dual complex is the dodecahedron. The duals of a vertex, right? The dual of a vertex is a circular graph. This produces here these cells, which then make up this CW complex. We find in combinatorics, we don't assume any Euclidean realization, except for visualization, of course. But this is a dual complex. Talked about this the last couple of weeks. We have a nice chromatology. So the chromatic number of the dual complex is always 2 or 3. This is a generalized Grudge theorem, not giving complete Grudge theorem. Grudge theorem is much harder. It's about planar graphs, and then also the vertex operator is always 2, which gives them an upper bound for the chromatic number of a q-manifold. What is also nice with this framework is that the Poincare duality is almost immediate, because you have these cells are kind of just, really dual to each other. So the F vector is just, reflected, and also the Betty vectors are just reflected, because the Hodge setup, the blocks are just reversed. And so this is the kernel, the dimension of the kernel of L0, that's B0. This only works if we have a orientable manifold. So this is just about how natural this thing is. The exterior derivative of in the complex is then replaced with the exterior derivative d star. Now to the definition of geodesic flow. So what you want to have is, first of all, a unique dynamical system. And so for every point and direction, you should have a unique geodesic. So geodesic should look somehow something like that. And I think, maybe because I played too much with this choice, that it's a good idea to look at the dynamics on the dual, on the facets. But you also need a notion of frame, right? When you have a classical geodesic flow, what happens is you have a natural frame bundle which is just attached at every point, right? At every point we have a basis. And what happens when you do geodesic flow, you actually have a notion of parallel transport. And that's not commutative, right? If you go along another geodesic, you end up with start with another direction, get to the same point, you end up with a different frame. And that also happens in the discrete. So what I propose in the discrete is to look at the direction or a frame bundle as just a permutation of the maximal simplex. This is very natural, right? Because if you have a tetrahedron, then what this is, this gives you just a point and 3 directions. That gives you a permutation. x0, x1, x2, x3, that gives this permutation defines you frame. Essentially, we can just work with ordered simplices, which we anyway do if we look at the, cohomology, for example. Do is we map this simplex, we map it just we cyclically rotate x1, x q minus 1, and then the first, instead of the first element here, x0, we just take the reflected element. So this is well defined because what you have is if you have a q minus 1 dimensional simplex, the dual simplex, which is the intersection of the unit spheres, right, of all the unit spheres here, unit sphere here, unit sphere, unit sphere here, this gives us 2 points. That's always the case in a q-manifold. And then we have just 2 points. So if this is x0, this is x0 prime. Now we have a new ordered simplex, and we can continue like that. But this is very natural, because if you look at this in the two-dimensional case, what you actually end up with, you end up with this triangle and this triangle, this triangle, this triangle, this triangle, and it really behaves like a geodesic flow, because the boundary curvature defined for a manifold with boundary, this is the boundary manifold curvature, this is 0. It's like a strip. It's interesting, you can play with this in a projective plane, for example. This can also close up as a Möbius strip, so it's not necessarily a cylinder, but it's can be a Möbius strip. In 3 dimensions, it's also beautiful. This example here, kind of one sees why the curvature is 0, right? So what you have is you have just 6 neighbors here. So this is the first tetrahedron, the second tetrahedron, the third tetrahedron, and so on. You are doing this Shashibo type chain. In the Shashibo case, it's a little bit more complex. You can actually not build this directly with that. The cube easier if I have cut it apart. It's also possible here, but it needs a little bit of skills. But that's the motivation for the geodesic flow. So what we have is a natural frame bundle. So there are f0 times q plus 1 factorial points in this frame bundle. There you can look at the number of geodesics which you have closed. Every geodesic, of course, is closed because it's a permutation. And so we have we can look at some statistics. And I did that for small manifolds and looked kind of what happens. It's natural for me also because what we have is somehow we have a structure where the geodesic curvature is 0. If you look at that here, the geodesic curvature, somehow, that's just the boundary curvature of the boundary curvature of that tube which we are looking at, and the tube which you do should not wind around, it should be straight, and so the curvature of the tube should be 0 dimensions. But it works in arbitrary dimensions. You can look at it in 4 dimensions. But another goal which I mentioned last time is the goal to define sectional curvature. And that's a little bit challenging, right? Because we have to get the notion of two-dimensional plane. If you have a two-dimensional plane, classically what you do is you let the geodesics move in every direction of the two-dimensional plane. You get a geodesic sheet. Now that geodesic sheet is not, if you start at another point of that sheet, that's not produces you another geodesic sheet. At the point, from every point, you have a unique geodesic sheet. Now, what happens in the discrete is, I think, a little miracle that it works. The radius 1 circle is just the dual circle of a bone, which is a q-2 dimensional simplex. So in general relativity, like Recke calculus, one has looked at the structure of, one has looked at bones or Recke curvature, which looks at the q-2 simplices. So in 3 dimensions, a q-2 simplex is just an edge, and then you look at all, and that's actually really kind of where the Shashibo thing comes in, right? We have this cyclic polytope, type of cyclic polytope. I mean, this is a cyclic polytope, but you can have a closed cyclic polytope. The dual is always a circle, right? That's where you would attach a two-dimensional ball, which is here kind of just a polygon, a field polygon. We are not looking at any geometric realization. So we have this natural notion of a circle, and that's our circle S1, which we will need in the curvature. Now we need a notion of circle of radius 2. Now that's where the geodesic flow comes in. What we can do is we can start at every of the facets, oriented facets of such a circle, and just look at the geodesic flow in the direction of perpendicular somehow to x. So if x would be kind of the thing, so you are perpendicular to that orange thing, and so you should get something like a disk. Now maybe it's best to see in the dual complex. What we have is we have a circle in the dual complex, which consists of this. This is this wheel graph is encoded as this circle. And now what we have is we have a degree 3. So there is one geodesic perpendicular to it. We do that, and then we close it with the shortest connection. What we will do here is actually kind of at every point here, we just close this. We close that. This looks like it's becoming three-dimensional, but it's actually kind of in a natural way, it's a kind of a two-dimensional sheet. What you then do also kind of in 3 dimensions, what you have is you have 2 additional directions which you can go to, and you fill these circles, and then you connect them with the shortest path. So then you look at the most outer circle made in 2 dimensions. It's easier to see, kind of in this case, it's the length of that circle. If the circle is just growing linearly, then this means flat. That's it for today.